Okay, welcome everyone to the first ZX seminar of the summer. And for our first talk, I'm going to introduce Haytham McDowall-Rose, who's going to talk about from fermions to qubits, a ZX calculus perspective. So take it away, Haytham.
Okay. Hello, everyone. Thanks for the introduction, Alex, and thank you to Sarah, who is not currently here, for the invitation to present in the ZX seminar. So today I'm going to be presenting this this presentation on some research that I did as part of my master's thesis last year, and research that has continued after that with Rosine and Leah on fermion-qubit mappings in the ZX calculus. And the paper is out on the archive as of today. You can look at it. I believe the link was sent around in the email for today's seminar. So so yeah, without further ado, let's talk a bit about fermion-qubit mappings. So one sec. So yeah, the structure of the talk will be roughly as follows. I'll talk about a bit of the background, so the fermionic background that you'll need to know to understand what a fermion-qubit mapping is. And then we'll talk about three main different types of fermion-qubit encodings. So we'll have the so-called linear encodings, which which are sort of the simplest ones. They come out of matrices over the field with two elements. Ternary tree mappings, which are something that was developed later, but has a quite interesting connection to ZX calculus, an interesting sort of tree structure going on. And then local encodings, which will help us solve certain problems about around the locality, or rather solving the non-locality of fermionic systems when we map them to qubits. So so yeah, let's uh let's first talk about a bit of the background of what all this stuff is and where it comes from. So yeah, um to motivate this, fermions are a type of subatomic particle. So they include stuff like protons, neutrons, electrons, I think neutrinos as well, but basically all the stuff that makes up atoms, which then make up all the other things, are, well, okay, not all the stuff, but a lot of it is fermions. So what we want to do with by studying fermions with a quantum computer is to use the quantumness of the quantum device to understand some quantum system in in nature. So we want to solve these simulation problems that are quite computationally expensive to solve on a classical computer. We want to do that on a quantum computer instead. So that's why we care about mapping these systems to qubits. Okay. Mathematically, though, how does one represent such a fermionic system? Okay, so the fermionic operators, these so-called AI, AJ, AI dagger, AJ dagger, you might have seen these before if you took a quantum mechanics class at some point. Essentially, I will show. I will. This is the basis that so it's a basis of bit strings that spans the fermionic Fock space. Let's say you have n, big N, fermionic sites numbered from 0 up to n minus 1. So this is n possible places that a fermion could be. The annihilation operator, AI, will, roughly speaking, remove or annihilate a fermion where there is one. So if you have a 1 in some position I in this bit string, the annihilation operator, I remember this because annihilation begins with an A. That's the only way that I remember which way around these go, AI and AI dagger anyway. The ith annihilation operator will lower that state from having a 1 in that ith position in the bit string to having a 0. And the creation operator will do the opposite of that. So if you take AI dagger and there's a 0 in position I in the bit string, the fermionic creation operator will create a particle there. So when we're dealing with fermionic systems, fermions moving from one position to another, a lot of what we imagine intuitively is we imagine operators of the form AI dagger AJ. So AJ will annihilate a fermion in position J, and then AI dagger will make another one in I. So it's like moving from J to I. It's called a hopping operator, that sort of term for that reason. We'll see those again later. But but yeah, this is the basic mathematical formalism, is that it's very similar to qubits in that we have a basis that's made up of bit strings, and we have these sort of standard operators. And the special thing about these operators is that they need to anti-commute with each other. So um, instead of commuting being when you swap them, nothing happens. When two operators anti-commute, it means that when you swap their ordering in a product, you pick up a minus sign, and that will be important because that is a lot of what creates some of the difficulties, the non-locality, the uh, heavyweight operators, which you'll see later. So what I've described here is one way of representing a fermionic system via having n creation operators and n annihilation operators. Equivalently, we can sort of change our perspective a little bit and work with these so-called Majorana operators, which we also have two n of. It's just that instead of we map them like this. For we have two n of these things that satisfy their own anti-commutation relation. And sometimes it's easier to work with Majorana operators than it is to work directly with creation and annihilation operators. And they're very closely related, as you can see. If you can the transformation is very easy to invert, going from Majorana to creation and annihilation. Okay, so we've talked about the motivation, why we want to do this, what these things are mathematically. Now, what is a fermion to qubit mapping? Well, I'm about to tell you. Fermion to qubit mapping it's an isometry from the fermionic Hilbert space that goes into the qubit Hilbert space. So it's it is what it says. It maps fermions to the qubits. The simplest example of a fermion to qubit mapping is the Jordan-Wigner encoding, which it doesn't do very much. Well, it looks like it's not doing anything, but it is doing something. This is taking the fermionic bit string. So we've got a bit string that's n bits long in the fermionic space. We simply map it to the qubit, the n qubit, well, bit string which is exactly the same. So it looks like the identity map, but it's not the identity map because it's going between two different vector spaces. And under this encoding, the Majorana operators, which are these things, they get mapped to these Pauli strings. So you can recover what the creation and annihilation operators look like. It's a big string of trailing z's, and then a sort of x plus iy, which is a projection operator on that sends ket1 to ket0 and ket0 to the zero vector. That's what the Jordan-Wigner operator creates. We'll see some advantages and disadvantages later of applying the Jordan-Wigner operator, the Jordan-Wigner encoding. But the main advantage that we see from the start is that it's very simple to implement. There's essentially nothing to do. In fact, formally, when we write M to be a fermion-qubit mapping from the Hilbert space of fermions to the Hilbert space of qubits, let's say we've got M qubits here, we implicitly are doing Jordan-Wigner under the hood. So while this whole thing here is a fermion-qubit mapping because it's going from fermions to qubits, the objects that we will actually study in this talk are the isometry that is going from qubits to qubits. Um, it's just uh, it's just that the Jordan-Wigner is happening implicitly all the time. So whenever you see a ZX diagram, it will be representing a linear map from qubits to qubits, but uh, but that's because we've already done the fermion to qubit part sort of trivially. I hope that makes sense. Does anyone have any questions about fermions or the fermionic background before I move on to talk about the ZX background? Well, silence is approval. Let's go. So the ZX calculus is something that we've all seen before. This is the ZX seminar, after all. In case you have never seen the ZX calculus before, it's a way of graphically representing linear maps on qubits, and you can uh, use the rules in this box to manipulate your diagrams to make them go from one form to another form. It's uh, it's convenient for a lot of things. Uh, yeah, and we'll need to use a couple of extensions of the ZX calculus to make fermion-qubit mappings make sense. The main extension we use is called the scalable ZX calculus, which is really useful for working with multiple wires at the same time. So instead of writing k wires with this dot 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 in between them, what we would do is express this as a thick wire with a label k. This represents a register of k qubits. And what we can also do is we can divide wires up that have that are on, say you have A qubits and B qubits, we can make a wire of A plus B qubits, and we can uh, split these wires up and fuse them together without doing any actual operations. Like these are just, identity maps, essentially. So yeah, this will help us to work with many qubits at the same time. And we will also need to define these thick-legged spiders. And we do that just by stacking a bunch of regular spiders on top of each other. So the states that go into a thick wire are states on, say, n qubits, or let's say k qubits since I used k here. So we apply uh the so that k qubit state is made up of products of states, and basically we just split those up and apply them to each of these spiders individually. Okay. There is one more piece of scalable machinery that will be very useful to us, which is these matrix arrows. So if A is a matrix over the field with two elements, we can define this map, the matrix arrow of A, will be the map that sends the bit string X uh, to the bit string AX, or A times X, so if X is a vector over F2, A times X is another vector over F2. And these things can be implemented by these matrix arrows in the ZX normal form, which you would have uh, you may have seen that if you have any phase-free unitary ZX diagram, it can be brought to this normal form here, where n equals n. It's a bit more complicated. We'll see later if you want to represent an arbitrary isometry. It isn't simply one matrix arrow, but there are ways to do it. So yeah, matrix arrows are very important for studying fermion-qubit mappings in ZX. Uh, you will see why soon. This is the rules of how matrix arrows interact with the other generators of scalable ZX. don't worry too much about this. It's mainly used in the proofs of how we the proofs of how we prove certain fermion-qubit mappings are equivalent. This stuff is all in the paper as well, by the way, which you can go and read on the archive. Is there anything else I need to say about scalable ZX or matrix arrows? I don't think so. But yeah, the takeaway from this section is that matrix arrows are very convenient because they allow you to, well, they compose nicely. You can push, Z spiders and X spiders through them. They have their own copy rules associated with them and their own sort of, you can stack them and break them apart very nicely and conveniently using scalable ZX calculus. So that's the end of the background section. Before I move on to talk about linear encodings, do we have any queries, questions? Great. Let's talk about linear encodings. So if you Google fermion-qubit encodings, these are probably the first kind that you'd come across. They are simply given by some invertible binary matrix, A, you map the fermionic vector F to the qubit state A times F, well, given by the bit string AF. And then I sort of I know I've been defining these encodings on a basis. So this is how a linear encoding acts on the basis of the Fock space. You just extend these by linearity over the complexes to define the whole mapping. I've been doing that implicitly this whole time. So if A, for example, were the identity matrix over the field with two elements, this map here would simply be the Jordan-Wigner encoding, which we've seen, which we love, which is very useful and very easy. Um, okay, and this linear encoding here is given by this matrix arrow because the matrix arrow implements the map from F to AF in qubits. And one thing I didn't mention is that for a matrix A, the connectivity between the Z spiders and the X spiders is given by you can read it off from looking at the rows and columns of A in a very nice way, which I won't go into here. Okay. In order to, well, encode, which is an operator. So let's say we have some operator, which is a fermionic operator, and we want to work out what it looks like under some fermion-qubit mapping. So here OJW is some operator that has gone through the Jordan-Wigner encoding. So it's already been mapped from fermions to qubits, but it hasn't gone through any sort of special encoding processes yet. What we want to do is we want to sort of we want to encode this by taking this Jordan-Wigner operator and pushing it through E without damaging E. And then whatever comes out the other side will be our nicely encoded operator. And the reason that works is because we can introduce this map here, well, E, a matrix arrow E, and then matrix arrow E going in the opposite direction. If E is invertible, these things will cancel each other out. So what we've basically done here is introduce an identity wire. And then if we look at this here, this is sort of, it's very analogous to just to a change of basis. We've got a Jordan-Wigner encoded operator, and then we have an encoding matrix, or rather an encoding circuit, and then the inverse of that encoding circuit on the other side. So we're changing the basis of our on which our operator acts. So yeah, pushing through the encoder is the crux of how we go from having a linear encoding to the operators under that linear encoding. Let's look at some examples of linear encodings then. We've already seen that the Jordan-Wigner operator is a linear encoding for, well, with matrix given by the identity over F2. There are a couple more. So there's the parity encoding, which looks like this. It's a bit more involved if you look at this ZX diagram than the Jordan-Wigner encoding. This is its matrix. It's got ones on and below the diagonal and zeros everywhere else. So what you can sort of see is that um, if you apply this this matrix arrow to some qubits, each each wire will end up storing the parity of itself and its previous wires. So let's say you have some, so you input the state that's like one, x1, x2, x3, x4, x5. If you put it through this circuit, what you'll get out is x1, x1 plus x2, x1 plus x2 plus x3, etc. That's what this matrix does. And this you can see that this thing sort of has this it has a recursive structure. Um, it's quite a simple recursive structure, which is well, every time you add another qubit, you simply add another row of ones at the bottom and another column of zeros. Or alternatively, you can read that as um, you have smaller encoders and then a matrix of all ones and then a matrix of all zeros this makes up a larger encoder. So you can see this scalable ZX diagram. What we've done here is taken this expression of which is a recurrence relation in matrices, and we've translated it to a recurrence relation of scalable ZX diagrams. I should have probably written that this is equal to the matrix arrow En. I didn't include that part of the picture for some reason, but yeah. This is a useful idea, the idea of turning these recurrence relations on matrices into recurrence relations of scalable ZX diagrams, and it can help us to learn a lot about um, the structure of an encoder. Let's look at a sort of more more interesting example. This here is the Bravi-Kitaev encoding. Now, this is special for a number of reasons. It has a similar, it has a recursive structure, just like the parity encoding did. The difference is that instead of adding one new qubit in each recursion, we double the number of qubits that we're acting on. So this encoder sort of has this tree-like structure, which will become apparent in a moment. Um, the special thing about this is that while the Jordan-Wigner operator has these trails of preceding z's, which can be as long as n, where n is the number of qubits, the Bravi-Kitaev encoding produces operators of weight log n, where n is the number of qubits. So what we gain from using Bravi-Kitaev is this exponential, well, up to exponential reduction in the number of gates needed to implement a fermionic operator that's been encoded in this way. And like I said, this here is the sort of tree structure. This is how the Bravi-Kitaev encoding doubles, if you will. It's to go from one encoding BK to the next one BK plus one, you stack them up and you do one CNOT gate. So the CNOT circuit form of Bravi-Kitaev is probably the most informative way to look at it. Um, yeah. Uh, there are more details about this in the paper, about the structure of Bravi-Kitaev. And you can, if you're more interested in graphical type, you can actually you can read my thesis. It has some more details about the shape of the encoded operators under under this encoding. But, but yeah, these are some examples. Now I will talk about some what linear encodings can do in general in a moment. But first, I want to talk about electronic Hamiltonians and what are they good for? Well, I'll tell you. An electronic Hamiltonian represents the interactions that are going on in inside an atom. So if you have an atom, it's got a nucleus, it's got some electrons. We've all got this mental picture in our head of what an atom looks like. Uh, and these um uh, these systems are governed by this Hamiltonian, which is given in terms of the fermionic operators. These H's, Hij, these are just coefficients. Um, these are constants relating to the exact strengths of the interactions in the system. Don't think about them too much, unless you're a chemist, in which case you should probably think about them. But what we can do is, if we want to understand an electronic Hamiltonian, we can put this in ZX using or under any linear encoding. If we just encode these creation and annihilation operators, we can put all of that together and we'll have an expression for our whole Hamiltonian. There's one thing though, we need to use this W node, which you may have seen. It's very useful for taking sums of diagrams, which is something you can't do in the ZX calculus without just putting a plus in general. But in the ZXW calculus, you can take sums and linear combinations and um, compositional combinations of terms in our Hamiltonian. And actually, what I've gone on and derived is under an arbitrary linear encoding. So here, E represents an arbitrary linear encoding. What these are, it's a list. It's a fully exhaustive list of all the kinds of terms that you can find in an electronic Hamiltonian. If you plug in an encoder matrix, um, this little table here will tell you how you should express um, that those particular components that make up that Hamiltonian, and that will help you express the entire Hamiltonian. For example, here's one I made earlier. It's the Hamiltonian for the hydrogen molecule under the Bravi-Kitaev encoding. It looks like this. Um, is it pretty? Kind of. Um, it's it's about as pretty as it would be if you wrote it out in Pauli strings, to be honest. Uh, but yeah, so some work has been done on using the ZX calculus to work with Hamiltonians. So yeah, if uh, if you're interested in this, I think that I suspect there are some problems relating to some unsolved problems that you could work on about uh, how to choose fermion-qubit encodings to work on a specific kind of Hamiltonian. But yeah, that's what linear encodings are and can be used for. They're simple because you just have to do linear algebra to work out the encoded operators. A side note is I've actually made a Python notebook that works out linearly encoded fermionic operators under an arbitrary encoding. Um, so that's been done in case anyone ever needs that in their life. I have it. Just text me. Uh, anyway, I feel like I should. How am I doing for time? Yeah, I think it would be good for me to move on and talk about ternary tree mappings. So yeah, ternary trees are uh This is to me the most interesting part of this actually is ternary tree mappings. Let's talk about what they are. This diagram looks a bit messy, but trust me, it makes sense. I will explain it. A ternary tree is any tree where each node has less than or equal to three children. So the children are the ones that come immediately after. It's just like in a family tree, you know, your children come after you. I guess there's no like, yeah, anyway. Yeah, it's the children are the ones in the immediate next layer. So so yeah, any tree that where each node has at most three children is a ternary tree. They don't. They can have. It can have. Any node can have zero children, or one child, or two children, or three, but it just has to be at most three. And so, given any ternary tree mapping, sorry, given any ternary tree, I can give you a ternary tree mapping, which is a fermion-qubit mapping, um, associated with this ternary tree. And it may seem a bit contrived the way this is done. So you look at the tree and then you traverse all the paths from the root node to the leaves, so the little fingers at the end of the tree. And if you look at all these paths, this big list of paths at the end of the ternary tree, um, you will put these together somehow, and these will give you the Majorana operators. If you remember earlier on, I said you could either represent a fermionic system by the creation and annihilation operators, or you can use this alternative basis, the Majorana operators, which are very closely related. And by mapping these Pauli strings to the Majorana operators, that gives you a fermion-qubit mapping. Okay, there is looking at this, there is no reason that this should work, but it does work. Trust me, I'll explain it to you. I will prove that this well, okay, I will not prove that this works, but it's in the paper. But the interesting thing is how this is philosophically very different to what we were doing before. Before we defined the fermion-qubit mapping as a map from one Hilbert space to another Hilbert space. Both Hilbert spaces looking a lot like C2 to the n, being having bases of bit strings. Um, the difference in what we're doing here is that instead of mapping the vector, what we did before is map the vector spaces and look at what the operators look like under that mapping of vector spaces. We're going straight to the operators. We're looking at we're starting with a tree, and we deduce what the mapping is from what the mapping looks like on this set of operators, the Majorana operators. And so there is a priori no reason that ternary trees would be related to linear encodings, right? Right? There's no way. Well, I'm about to surprise you all. That they are okay, not yet, but soon. We can translate ternary trees to ZX diagrams. Yeah. So there was some work going on at the same time as I was writing my thesis about fermion-qubit mapping. A guy called Mitchell in Cambridge was finishing his PhD, and the last paper he wrote was uh, had the title "Ternary trees are linear encodings," which is a bit shocking. I was like, "What? There's no way a ternary tree will give us every ternary tree has an associated linear encoding, and a linear encoding is just a scalable ZX diagram." But yes. Every ternary tree has an associated scalable ZX diagram slash matrix arrow, depending on how you want to look at it. Uh, this is the translation. I will show you what this means, though. Here's the example ternary tree that we made earlier. We want to look at what the linear map that is associated with this ternary tree encoding is. So we have maps on vector spaces and we have maps on operators. This here is the map on operators. I haven't told you exactly what this does to the operators, but these are the Majorana operators, and knowing what those are gives you enough data to know what the linear map is on the vector space itself. Uh, so you can see sort of these shaded blobs around around these parts correspond to the nodes of the tree. Uh, and by replacing each node in this tree with this ZX diagram, what we get is a big old tree of ZX diagrams, which we may simplify. Let's do it. We simplified it earlier. If you apply some little ZX rules, you can yeah, just massage this out, and you end up getting this encoder, which I haven't shown it here, but if you work out what the creation and annihilation operators are by pushing them through this encoder, it will give you exactly um, the Majorana operators, which are given by this set of Pauli strings, which is amazing, actually. Like there is no reason this should be true, but it is. Well, okay, there are reasons it should be true, which are the proof, which I'll hint at later. So yes, let's look at some examples of some more examples of some ternary trees for some encodings that we've seen earlier. The Jordan-Wigner encoding, yeah, yeah. It just gives you back the identity. This is its ternary tree. It's I haven't labeled the legs of the tree, but we always take X, Y, and then Z in that order, just by convention. Uh, so say if we look at any any um any root to leaf path, it corresponds to the Pauli string you get from traversing X, Y, Z like that. So this is X4, Y1, Z2. Aha, there we go. I probably should have made that clearer at the start. Yeah, if you're confused about where this pile of strings comes from, it's through traversing the tree. So here's Y4, X7, X5. Whoa, wow, amazing. It's there. And these will be the Majorana operators. Okay, back to looking at the examples. So yeah, Jordan Wigner, it all just everything disappears and it's the identity. Parity, um, is it's quite similar to the Jordan Wigner actually. It's just that the tree goes up instead of going down. Uh, it's that's quite interesting how that happens. Braivi-Kitaev, the sort of inductive tree structure that we had before with the matrices, where you double the size of the matrix and then add ones along the bottom. Instead, what you do to level up the ternary tree is um, you simply add uh, you add another layer of qubits. So here we've gone from we have 8 qubits. If we wanted to go for 16 qubits, we'd add 8 guys on the end. So we'd put them 1, 2, 3, 4, 5, 6, 7, 8. We leave off the middle ones. That's how the translation works. And if you step through the let's go back a moment to look at this rule for translating ternary trees to ZX diagrams. We've applied that to Braivi-Kitaev. Um, we've just replaced all these ternary trees with the ZX diagrams, and if you step through the calculations, you can get back to this ZX normal form, which is if you look at the rows and columns of this matrix, this is exactly the matrix whose arrow will be this. In fact, you can let's look at the top four. Let's look at the first four blocks of this even. It's so one is connected to one, 2, 4 and 8. 1, 2, 4, and 8. 2 is connected to I'm sorry, wait. 2 is connected to 2, 4, and 2, 4, and 8, etc. You can look through this in the paper if this is if you think this is interesting about how these two things are related. But let's talk a bit about the proof. So the main theorem of this paper is that this translation of ternary tree to a scalable ZX diagram is in fact correct. Uh, and the way that we prove this is by induction. So if you can induct on the height of the tree, essentially because if you look back at the way we got these Pauli strings is by traversing the tree from the root node. If, say, we're working on a tree, we can have its root node and then separate it into three different subtrees. We already have root to node Pauli strings for the subtrees. We simply add one more Pauli string onto the front of those to get the total tree. The only thing left to check is that those resulting Pauli strings from adding this one extra operator on are the same that you get from pushing through the encoder that is made out of these things. And that takes a bit to check. Okay. So yeah, this is proven in detail in the paper. You can read the proof of why this is correct, but I've sketched the idea of how you do it. It's by pushing through the encoder, which is a great technique. Okay. And this is our other theorem about which tells us how we can go from a ternary tree to a linear encoding. So this theorem had been proven. Mitchell proved this theorem. Mitchell from Cambridge proved this in his thesis without using ZX, and then around the same time, shortly after he published his, he we found a proof of the same result, but we gave a diagrammatic proof, which also gives us this scalable ZX tree in the process. So if you look at this ZX tree here, let's say EX, EY, and EZ are the encoders for the subtrees. We can throw all of this together and get a matrix out of it. And if we keep doing this inductively down until we've reached the leaves of the tree, that is this algorithm here, which given a ternary tree, gives you back the matrix associated with that ternary tree. This I have not coded this, but yeah, it shouldn't be too hard to. I mean, this is literally the pseudocode. So yeah, that's how this is how you translate between ternary trees and linear encodings. So yeah, what we've shown is that ternary trees are a subset of linear encodings. The converse is not true though. There exist linear encodings which do not arise from a ternary tree. Um, yeah, so it's not quite an equivalence, but it's interesting that one is inside the other, considering how different they look at the start. Okay. That's the end of the ternary tree section. How are we doing for time? Okay, 49. Okay, I've been going for quite a while then, 45 minutes. Okay. Let's to wrap this up, let's quickly talk a bit about linear encodings. Does anyone have any questions about ternary trees? Anyone at all?
I had a simple one just about the ternary trees and their mapping to Majorana fermions.
Mhm.
Is so from what I gather, you just have a you if you enumerate your Majorana fermions and then the as drawn in your diagram, the order in which those Pauli strings are mapped to the Majorana fermions is via their enumeration.
Um, yeah, that's something I kind of glossed over. The way that these Majorana fermions, so this is a if we look at let's look at the example. So if we go back to this tree, um, it's a bit more technical. It, the short answer is that it's in the paper. The slightly longer answer is if you want to work out the Majorana operators that are sort of related to the creation and annihilation. So let's say Majorana operators 2n and 2n plus 1 come from looking at the nth node in this tree. So let's say you want to look at Majorana 2 and Majorana 3. They are both descendants of 1. I believe it's you go all x's until you get to a z, and then all y's until you get to a z. It's yeah, it's not an obvious way to do it, but it's in the paper.
Oh,
Yeah,
cool.
how
Yeah.
it's a bit complicated, and I tried to avoid talking about it because it would add more confusion to the trees.
Yeah. That's good
Could
to know
make a
though.
joke about.
It's non-trivial.
Yeah, yeah. I was trying not to lose the forest for the trees, shall we say? Anyway, um, next we're gonna finally finish this up by talking about local encodings. Um, okay, so yeah, the issue that we have with these fermionic operators is that once mapped to qubits, the we have these strings of z's. I'll show you what I mean. We have this. Let's say we want to look at a hopping term, just a good old-fashioned operator that takes a fermion from fermionic site Q to fermionic site P. We've got a under the Jordan-Wigner operator, we've got this big string of z's going all the way from Q to P, and that's once we've picked an ordering of how we're going to order our fermions. We have to have one of those at the start. Otherwise, how will we know where to put the z's? But yeah, anyway, the thing that we want to get rid of is these big chains of z's, or we want to at least make them smaller somehow. So yeah, we are sad because our local interactions, it's P and Q. They're how they're friends. They're just two fermions, but they get in mapping them to qubits. We have to act on all these other qubits as well, which we'd really prefer not to do. So how do we fix that? Well, as is usual in maths and in life, there is no such thing as a free lunch. In order to sacrifice, well, to get rid of these chains of Z, we must sacrifice something else. So in our case, generally we add these ancilla qubits. So we need to use more qubits, which sometimes is fine. It's okay. We just have to try not to use too many of them. And we do this using stabilizers. Now, this is the definition of a stabilizer, in case that word is not familiar. It does what it says on the tin. It What you do is a stabilizer is something which if you do it after your encoder, so it's a qubit operator where when you do it after the encoder, it doesn't do anything. It doesn't do anything to your encoded stuff. It vanishes. It's like a ghost. It passes straight through. And these will be useful. We hope that our stabilizers can be used to cancel out some of the Zs for our encoders. Okay, so yeah. By the way, this is the most general phase-free ZX diagram given going from k qubits to n more than k qubits. this is what it looks like. You have to add this little matrix arrow dangling off the end. Um, a lot of the encoders we work with will be in this form. You can also extend to a bigger class of encodings where the encoders are Clifford circuits, and this is what that would look like. I won't talk too much about this because I do wanna wrap up soonish, but yeah. Um okay. Let's look at this example. We've got a fermionic system which is on a 2D lattice, and what that means.
Did anyone else lose Haytham, or is that
Yeah, he's frozen for me too.
okay? Let's see if he recovers. Okay, I'll drop him an email and see if he's in contact. It was probably just a bad connection.
Rosina's trying to message him.
Okay.
See if I can get back. Maybe he can like hotspot or something. But we can wait a few minutes and if
Yeah,
need be,
fine,
resume.
No,
Think it's good? Okay, we're good. We're good. Resuming soon.
Hello everyone, I'm back. Technical difficulties. Not sure what happened there. Might have been the mice chewing on the Wi-Fi cables again. It always seems to be. Anyway, I will. Not sure where. Oh, back at the start. Not sure where I was when wh- when when you stopped hearing me. But let's go to this slide. Can everyone hear me fine? Am I
Yeah,
audible and
I think you're good now.
visible?
We can
Or
hear
is
you, but we can't
Okay.
see your slides.
yeah, we can't see the
Oh,
slides.
yeah. That's because I haven't shared my screen. Thank you, Martian and Alex. Yeah, silly me. Okay, back to PowerPoint. Okay,
Yeah,
cool.
that was the slide we were on.
Okay, great. So yeah, what this means, and what it means to have a 2D lattice of fermions is that we have this square of fermions where the all of the interactions that take place in the problem are between fermions in this square and fermions which are adjacent to each other in the square. So 2 is adjacent to 7 in the square, but it's not adjacent to 6. We're sort of taking this, some people call it the Manhattan distance of 1 away from the each fermion. That's the ones that it interacts with. This blue line here represents the ordering of the qubits. Sorry, I said qubits again. These are not qubits yet. They're about to be. Foreshadowing. So, um, so yeah, the Jordan-Wigner encoding essentially looks like a 16 identity wires. That's what these are. Each of these is an identity wire corresponding to 1 qubit. So, we'll have qubits for each of these fermions. Uh, and uh and yeah and but yeah the relaxation that we've had here is that we only allow these interactions between adjacent things. Before we allowed any interaction between any fermion and any other fermion, but here it's only allowed in the square. Okay, what does this relaxation get us? Well, if we add these ancilla qubits, so these 1 through 4 prime, if we have these outputs, these these X nodes are output only. So we're sort of mapping 16 fermions into 16 plus 4 qubits, which is and we want to do that because it will help us somehow. Now, if you remember what I said about stabilizers, if we can get a stabilizer that will cancel out those trailing strings of Zs, that would be very helpful because we wouldn't have as many Zs hanging around. But luckily, wow, look at this. If you look at any of these blocks of five things, these 4-qubit to 5-qubit maps, if you put a Z at the end of each of these wires, say Z, 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 the Z on this red one will copy through and hit each of these 4 green Zs over here, and then we'll have 4 Pauli Zs that will cancel with these 4 Pauli Zs, and the whole thing will disappear. So we found a stabilizer that's it's a string of 5 Zs, and we can put those 5 Zs in here, anywhere. Well, not anywhere, it has to be all 5. So if you look at bearing that in mind, these 5 Zs, we're about to see something really cool. Let's look at this example where we're trying to encode the hopping operator between fermion number 3 and fermion number 15. So this is quite a long string of Zs. It's Zs all the way from number 4 to number 14, and it's in this sort of snake pattern because that's just the pattern that we're using for the connectivity of fermions, or the ordering of the fermions. But because this encoder has a stabilizer, we can put these racks of Pauli Zs onto this encoder, and after tacking those on, most of these cancel. So what we've done in this equality is put these racks of Pauli Zs on each of these things here, and we've gone from an operator that has to act on what's this, like 13 different qubits, to less than that. It's 9 qubits. So instead of going like that with your snake just goes like that. To go from 3 to 15, we've shortened the path, and in doing so, we've shortened the amount of intermediate Zs that we need to implement this. Okay, let's look at another example of a square lattice of fermions. So what we did in this previous case was we added 1 column of ancilla qubits to the square. There's another way to do it where we add a row of ancilla qubits between each row of fermions, which I'll show you how it works in a moment. We're going to build an encoder that has these stabilizers given by these squares of x's and y's. So if we let's look for a moment at this slide here. Given you can read off the stabilizers of this diagram by looking at these plaquettes. So if you look at the let's say the squares x, y, x, x, y, x, if you look at the way these qubits are numbered, 1 bar, 2 bar, 1, 2, 1 dash, 2 dash, this has the exact same stabilizers that you can read off of this diagram. You can read off by looking at the sort of what am I saying? You can read them off of this picture, because if you look at this, it's just it's a single Z in the middle, and there's the ZX calculus rule where if you push in x's into a Z from all the sides, they cancel each other out. It's that rule essentially, but it looks more interesting. So yeah, what we've done with this encoder is we've added a lot more ancilla qubits. And what that's given us is it's given us this big stabilizer here. Uh, and if you look at this diagram, this figure, which is in the paper, you can see that we've got the same geometry representing the connectivity graph of these fermions and these qubits, and this square of squares full of stabilizers, and the actual ZX diagram. Yeah, I maybe should have said more clearly that these wires represent we do input at the top, output at the bottom, and the ones that have no wire coming into the top are just output ancilla qubits. And you might recognize this picture if you've seen the surface code from quantum error correction. Um, the difference being here that in the surface code you encode a single qubit or into a grid of qubits, a single, yeah. So you go from one qubit to a square of qubits. But here we're going from a square of fermions to a square plus some more rows of qubits. So it's slightly more complicated, but the geometry is very similar. And there's still some work, I think, to be done on local fermion qubit mappings that could be quite interesting because this is something we came about quite late in the research and the writing of this paper. So yeah, I shall wrap up in a moment. In conclusion, yep, this is the last part. We've used the ZX calculus to do a lot of things. We've studied linear encodings, ternary tree encodings, and local encodings in this common language. Sometimes we use scalable, sometimes we use, just the matrix arrows. Sometimes we use these plaquettes, but it's all essentially in the same language, which is kind of surprising how the ZX calculus links these representations that seem like they're all very different from each other, which they are very different from each other. I mean, we talked about how the ternary tree encoding comes completely out of left field if you've been looking at linear encodings your whole life. In the future, what would be interesting for us to work on could be problems related to using the ZX calculus to find optimal mappings for a given situation. So given some sort of uh, some Hamiltonian with some constraints and some sort of special information about what interacts with what. Um, you can are there ways to find optimal fermion qubit mappings somehow? Another thing that would be interesting would be to see how the characteristics of fermion qubit the mappings themselves correspond to the properties of their diagrams in ZX, and also to look more into the connection between quantum error correction and fermion qubit mappings because well uh yeah, some similar techniques are used to quantum error correction. For example, the scalable ZX recursion stuff, uh and also the surface code looking squares. And one more thing is that using the Focked up ZX calculus, we can maybe study bosons as well, where the difference with bosons is that instead of having two levels, 0 and 1, we have levels going 0, 1, all the way up to all the integers. So we need an infinite dimensional space, and to do that, we would need the Focked up ZX. So yeah, that's all I have to say. Thanks, guys. Do we have any questions? Oh, you're clapping, but I can't hear any of you. I don't know if this will be on the video.
Yeah. Everyone do the clap emojis and round of
Oh
applause.
wow.
Yeah, thank you, Haytham, for the great talk. Yeah,
Thank you.
and as you mentioned, the floor is open to any questions.
Wow. Hey, Leah. Oh, she's gone. Anyone? Oh, is someone?
I don't see any hands up, but I have a question
Hi.
regarding the connection between the quantum error correction and the mappings. I was just
Hmm.
thinking, what sort of interplay do you see happening there?
Honestly, I don't know that much about quantum error correction, but um, the the types of encoders, the fact that we're working on usually going from fewer things encoding into more things uh, in quantum error correction as well. There's probably some way to like what am I saying? What am I trying to say?
It's like
I'm trying to say,
excellent.
I'm trying to
Can
say
you
to
can you hear
use.
me?
Oh, Rosine, yeah, I can
Can
hear
I
you.
also add to your answer? So I think one area where this comes up is you can try to do like, so because you have stabilizers that are trying to cut out the Pauli string, but you also have more things. You can come up with codes for fermionic simulation that are more optimal, that can like somehow do both two things at once, and you can have like you can do quantum error correction at the same time while doing mappings and try to get more optimal codes that are optimal for doing fermionic simulation. And there are already some work that explore this, but yeah, I guess probably do more there.
Oh, I see. When you say optimal, do you mean in terms of things like code distances and the number of physical qubits?
Yeah, so like so there's distance, which is which is what you want from the error correction side, and then there is locality, which is what you want from the fermion-to-qubit side, and those are not directly related goals, but you want to try to make them like yeah, you want to try to find codes which can do both things at once somehow.
Nice. Yeah.
Like increase distance for error correction. It's in,
Thunderstorm here.
Apology if there was a big bang on my microphone. There's a thunderstorm outside. I don't know if anyone heard that. Um,
I didn't
yeah.
hear it.
Oh, cool. The Zoom microphone thing must be quite good then. Um, yeah, and it kind of related to the same question is, so there's a bridge between it sounds like the fermion to qubit mapping is quite good for finding these error correcting codes. Do you have any, because there's a lot of work on ZX calculus for error correction, is any of that useful for the fermion to qubit side of things? So do you see the research in this paper being informed by like error correction stuff?
It
like,
wasn't really
oh, sorry, go ahead.
like in the local encoding section, yes, but for most of this, I don't know a great deal about quantum error correction, and it's still like yeah, it's this is still quite accessible to someone without that knowledge. Uh, Rosine, do you? I mean, you know quantum error correction better than I do. Do you draw these parallels in your head?
Yeah, I mean, for the local encodings, when we were trying to come up with encoders for local encodings, so it's basically drawing on the work done in ZX for error correction. So we're just trying to like see, okay, how do we do this? Like we have these stabilizers that we want to describe. And it was basically, we were just basically taking like the ZX for error correction work and trying to bring it to local encodings. And I think there's a lot more to like uh, borrow from the error correction sides and apply it to the local encoding side to like for like better encodings and like so this is like the things that we considered here were just the two simple examples known in the literature with like the 2D square lattice, for example.
Yes, but translating it was really hard. It's really
Yeah.
hard to do.
But then there is like a lot more complicated Hamiltonians where you have more complicated connectivity graphs and like that we haven't really explored anything there. And I think it's probably also related to like yeah, I don't know, I feel like maybe there's also some connection we can like to get to like graph code somehow.
Yes. In fact, I don't think. Hold on. Okay, Thunder's good. So next month, DX seminar, I'll give a talk on our new upcoming work on any Clifford isometries, the new normal form for in the ZX calculus. This work was like intended for and starting from our quantum error correction work. We're looking at, instead of just CSS code normal forms, we're looking at any stabilizer code normal forms. So some of that was what informed how we did this local encoding, where the connectivity of the graph lets you read off the logicals and stabilizers in this work. And so that was part of the same, I think, research direction. And because these are looking at any Clifford isometries, so any stabilizer ZX diagrams that are isometries, then that happens to also be what the any fermion-to-qubit mapping will also be such a that is mapping Paulis to Paulis would also be, so Pauli-based mappings would also be this kind of Clifford isometry. So that's why it looks similar, because it is the same mathematical object.
Yeah, and it would be really cool to like see if you can like connect directly the interaction geometry, which is like how different fermions interact in a graph form, to like error correction codes like via ZX as the middle thing. And like there's intuition that must be related to those codes
Yeah.
the I mentioned.
What's interesting is that well, maybe I shouldn't say too much, because we're talking a lot, but the pocket diagram that was in the that example of the square lattice AQM, that just shows the stabilizers. But when we draw an encoder, we also need to say how the logicals work. So we had to like calculate what is the logicals in this case, so that we could get an encoder diagram. So that was something additional in the ZX picture that required us to calculate extra information.
Oh, I see. That's really cool.